In this movie, we're going to discuss how Hodgkin and Huxley calculated the time course of the sodium and potassium conductances and their voltage sensitivities from voltage clamp records. In the last movie, we saw how Hodgkin and Huxley could measure the currents flowing across the membrane of the squid giant axon when the membrane potential was clamped and thus fixed at some predetermined value. In this record here, the value was minus 10 millivolts. From the currents evoked under voltage clamp, Hodgkin and Huxley made two additional calculations. One, they calculated how the sodium and potassium conductances varied during the action potential. And two, they calculated how the sodium conductance and the potassium conductance were each regulated by voltage, that is, by the membrane potential. To make those calculations, they first separated the sodium and potassium currents by using two different channel blockers. The first is tetrodotoxin, abbreviated as TTX, which selectively blocks sodium channels. And the second is tetraethylammonium, abbreviated as TEA, which selectively blocks potassium channels. So I'd like to take a moment to illustrate to you how these channel blockers work. And to do that, we're going to go back to the voltage clamp, and we're going to clamp the membrane potential at minus 10 millivolts. And then what we're going to do is I'm going to add tetraethylammonium, or TEA, to the extracellular fluids and block the potassium channels. And you can see them blocked there with TEA. Then I'm going to take this in slow motion because I want to make a few points that will illustrate how we're going to measure conductances. So the first thing that happens is that the sodium channels open because the membrane potential is depolarized, and as a consequence you get an inward flow of sodium current. I'm going to stop it here. And the point I want to make is that the driving force on sodium, that is the difference between the membrane potential, which is minus 10 millivolts, and the sodium equilibrium potential, which is plus 55 millivolts, is constant. It's not changing because the membrane potential isn't changing because we've clamped it. As a consequence of that, the only thing that's regulating the flow of current through the sodium channels is its conductance, whether or not the channels are open. So in other words, the currents flowing at any time are a proxy for the conductance at that time, because the driving force, the difference between the membrane potential and the equilibrium potential for that ion, is held constant. So just by looking at the currents, we can estimate what the conductance changes are. But of course, they're going to be scaled by the driving force. I'll explain that in a few moments. So now, the inactivation gates close, and that's what we see. The current goes to zero. After that, of course, the potassium channels open, but nothing can happen because they're blocked. There can be no outward flow of potassium current because the TEA is blocking the channels, and that's what the record looks like. Now, let's turn to adding tetrodotoxin to the extracellular fluids and block the sodium channels. So now we clamp the membrane potential again at minus 10 millivolts. So what happens at first is the sodium channels open, but there can be no sodium current because the channels are blocked. Hence, the record is flat. A moment later, the inactivation gates close, and then the potassium channels open. And the same argument can be made for the potassium channels. The only thing that's modulating or regulating the amount of current that's flowing through the potassium channels is their conductance. If their conductance is high, a lot of current will flow. If their conductance is low, very little current will flow. So these are the currents measured in the squid giant axon when the membrane potential was clamped at minus 10 millivolts. There is a pure inward current carried by sodium, and that's the current one sees when you block the potassium channels with tetraethyl ammonium. And then there's a pure outward current carried by potassium. And that's the current obtained when tetrodotoxin blocks the sodium channels. And then, of course, there's the total current, the current that would be obtained if you didn't have any channel blockers at all. The currents that we're going to be interested in, and the ones that we're going to use to compute the conductances, are the pure currents. The inward current carried by sodium and the outward current carried by potassium. Okay, now we're going to start and get down to business. And we're going to consider how these pure currents, the ones shown in the upper right, the sodium current and the potassium current, can be used to calculate the time course of the sodium and the potassium conductance. And we're going to start with Ohm's law. And in case you don't remember Ohm's law, you can go back to the electrical equivalent of the axon, one of the movies. It's fully explained there, but it's simple. All it says is current, the amount of current flowing, is going to be equal to the conductance, the ease with which it can flow, times the driving force, the thing pushing it through. And now we're going to transpose terms such that conductance, because that's what we're interested in, is the conductance, it's abbreviated little g, is going to be equal to the current divided by the driving force. And the driving force, of course, is nothing more than the membrane potential minus the equilibrium potential for that ion, which either could be potassium or sodium, and it's fixed. It's a non-varying quantity in voltage clamp. It's constant. So for sodium, the driving force is minus 10 millivolts, that's the membrane potential, minus 55 millivolts, the equilibrium potential for sodium, which equals minus 65 millivolts. That's the driving force. And for potassium, the driving force is minus 10 millivolts minus 75 millivolts, which is going to be equal to plus 65 millivolts. The driving forces are the same. And the only thing that the sign says is that potassium is driven out of the cell, that's why it's positive, and sodium is driven into the cell, that's why it's negative. Okay, we're going to move the conductance over here, so we make some room for it, and we're going to look at the conductances of potassium. And so it's equal to the potassium current divided by the driving force. But we know the driving force. The driving force is plus 65 millivolts, and it's going to stay plus 65 millivolts because the membrane potential isn't changing. We've clamped it. And the equilibrium potential, of course, isn't changing. So the conductance is simply equal to whatever current we measure, potassium current, divided by plus 65 millivolts. And let's see how that's done. Let's plot it in this graph. So the first thing we're going to do is we're going to take a point in time, and we're going to measure the current at that point in time. That's the current at the arrow, and we're going to divide that current by plus 65. Now in this case, the channel hasn't opened, so the current's 0. So 0 divided by plus 65 is going to be 0. And the next thing we're going to do is we're going to take another point in time, and we're going to divide that current by plus 65 and plot it. That's its value. And then we're going to take a third point, and we're going to divide that current measured at that point in time by plus 65 and plot it there. And we're going to do it for all the points along the current curve. And we're going to get the conductance. And all that's saying, you can see the conductance curve looks just like the current curve. It's got to. The only thing that's modulating the amount of current is the conductance. So the conductance for potassium is nothing more than the current for potassium divided by or scaled by the driving force. That's all it is, and that's why it has the same shape, nothing more. Now let's plot the time course of the sodium currents. And we're going to plot those time courses just above the time course of the potassium conductance in the left-hand side. And we're going to do it exactly the same way. The conductance for sodium is going to be equal to the sodium current at any point in time divided by its driving force. And we know its driving force is minus 65 millivolts. And that's going to remain constant. We're going to do the same thing that we did for potassium. We're going to take a point in time, the current at the arrow, we're going to divide it by minus 65, and we're going to plot it. And then we're going to take another point in time and take that current, this is the peak current, and divide it by minus 65 and plot it. And another point in time and plot that current divided by minus 65 and do it the whole thing for the whole current curve. And that's what the conductance curve is going to look like for sodium. It was from these conductance records of the time course of the potassium conductance and the sodium conductance that led Hodgkin and Huxley to propose how the sodium and potassium channels must be working in conjunction to produce an action potential. Let's look at the sodium conductance first. It jumps up immediately. They therefore proposed that it must have an activation gate that opens quickly upon depolarization. But then the conductance goes down, so they postulated that the sodium conductance must also have an inactivation gate that automatically closes the conductance even though the membrane potential is still depolarized and isn't changing. Now look at the potassium conductance. The potassium conductance is slower than the sodium conductance. Look at the time course of the opening of the sodium and potassium conductances. The peak of the sodium conductance occurs when the potassium conductance barely even started to open. From the conductance disparities in time, Hodgkin and Huxley proposed that potassium conductance must also have an activation gate, whose opening is slower than the opening of the sodium activation gate. At a slightly later point in time, you can see the sodium conductance is going down while the potassium conductance is going up. This told them that the time course of the sodium inactivation is about the same as the time course of the potassium activation. They are occurring simultaneously. It was these kinds of conductance records that provided the insights into the kinetics and the cooperative way in which sodium and potassium channels work. And that cooperative activity is the ionic basis of the action potential. But they also wanted to know how the conductances change with membrane potential. After all, these are voltage-sensitive conductances. In other words, what are the voltage sensitivities of the sodium and potassium conductances? And in order to do this, they were going to look at the peak conductances of sodium and the peak conductances of potassium. In this particular record, the peak conductances were obtained at minus 10 millivolts. But what they really wanted to know was how do these peak conductances change over the whole range of membrane potentials that the neuron would normally experience. So the way they did this was to generate the various currents, the sodium and potassium currents, at a variety of different holding potentials. In this case, we're going to generate it at a holding potential of minus 30 millivolts. So the membrane is clamped at minus 30 millivolts, the current record is obtained, and then the peak sodium conductance is calculated from the simple equation of the peak sodium conductance is equal to the peak sodium current divided by the driving force, which is minus 85 millivolts in this case, and the peak potassium conductance is equal to the peak potassium current divided by its driving force of plus 45 millivolts. Then do it at a different holding potential, in this case plus 20 millivolts, derive the current, and then calculate the peak sodium conductance and the peak potassium conductance from their equations. And in fact, we can do this at all the different holding potentials and generate the currents and then derive and calculate the peak sodium and peak potassium conductances at every one of these holding potentials. And that's what they did. These graphs show how the peak conductances, the number of open potassium or open sodium channels, vary with membrane potential. The graphs are sigmoidal in shape. That is, at very low membrane potentials between minus 60 to about minus 40 millivolts, each small change in membrane potential only causes a correspondingly small change in either potassium or sodium conductance. However, at more depolarized membrane potentials from about minus 40 millivolts, the curves rise sharply so that each small change in membrane potential evokes a large change in conductance. The sigmoidal shapes of the conductances also explains why the action potential is evoked only at threshold level of depolarization. To appreciate threshold, look at the curve for sodium conductance. When the membrane potential changes from rest at about minus 65 millivolts to about minus 40 millivolts, there is only a small change in conductance, and hence only a small influx of sodium will occur. The small amount of sodium influx is not sufficient to generate an action potential because any entry of sodium is offset by an efflux of potassium ions through both the leak, that is the non-voltage gated potassium channels, and then through the voltage gated potassium channels that open a moment later. If the membrane is depolarized to about minus 35 millivolts, as indicated by the arrow, the slope of the conductance curve is now steep. This means that each small increment in membrane depolarization now generates a larger conductance increase, and hence a larger influx of sodium than was generated at lower membrane potentials. This influx of sodium is now greater than the efflux of potassium through the non-voltage gated potassium channels, and the net gain in positive sodium ions further depolarizes the membrane. Due to the steep voltage dependence of the sodium conductance, each increment in depolarization generates an even larger sodium conductance, and thus an additional influx of sodium ions. The additional influx of sodium further depolarizes the membrane and evokes an even larger sodium conductance, and this continues until the maximum sodium conductance is achieved. All of this happens very rapidly, before the inactivation gates can close and before the slower activation gates in the potassium channels can open. Thus, the positive feedback, whereby additional sodium entry generates progressively larger sodium conductances, accounts for the upstroke of the action potential. So now, let's spin all of this together. The voltage sensitivity of the sodium and potassium conductances shows the membrane potentials at which the sodium and potassium conductances are activated, and the degree to which they are activated at each membrane potential. These features explain why an action potential has a firing threshold, and why sodium channels open progressively more as the membrane depolarizes, and thereby accounts for the upstroke of the action potential. They also show that potassium channels, just like sodium channels, also open progressively with depolarization, thereby accounting for the repolarization of the membrane. However, the voltage-sensitive events only make sense if they occur in the proper sequence. The way these events are orchestrated in time is explained by the timing of the conductances, where the activation gates of sodium channels open first, followed shortly thereafter by the closing of the sodium inactivation gates and the opening of the activation gates on the potassium channels. Together, voltage sensitivities and timings of the sodium and potassium conductances, discovered by Hodgkin and Huxley from voltage clamp experiments on the squid giant axon, account fully and completely for the events that underlie the generation of the action potential.